class, we are now on 7.3c, the mole concept and balanced equations, limiting reagents. So we introduced the concept of the mole and how we can use the mole with balanced equations to relate to the amount of one substance to the amounts of all the other materials in that equation that are consumed or produced during the reaction. So examples, we look at the amount of HCl involved in this reaction with iron, we can determine the amount of iron needed to react with it, or the amount of iron 2 chloride or hydrogen gas that is produced. So through one, we can figure out what the other amounts were either produced or consumed in this reaction, which is good because you don't want to either put too much or too little and then not get the full reaction. Think of it as baking a cake. You want to make sure you have the correct amounts to have that cake come out properly. And without that, if you put 1 egg versus 2, or you don't put oil, something that's missing, you're not going to have the results that you want. Okay, so the perfect example. So in this section, we're going to look at a limiting reagent. We see how the limiting reagent determines the amount of a product that can form and how to determine the limiting reagent for a particular reaction. With this example, this is a sandwich. Hopefully everybody knows what that is. In order to make a plain, which is dry, turkey and cheese sandwich, we need 3 ingredients. We need bread, we need turkey, and we need cheese. When we combine these ingredients, you get a dry sandwich. We could write this like a chemical reaction. We have 2 slices of bread plus 1 slice of turkey plus 1 slice of cheese equals or produces 1 sandwich. This equation gives us not only the recipe for making 1 sandwich, it also gives us the ratio for making many sandwiches. If we were to make many sandwiches, such as for 100 people, we would still follow the same ratios. So let's take a look here. If you have 80 slices of bread, 18 slices of turkey, and 15 slices of cheese, how many turkey and cheese sandwiches can you make using this recipe? So we have 2 slices of bread, 1 slice turkey, 1 slice cheese produces 1 sandwich. In that, we have for bread, we have enough bread for 40 sandwiches. We have enough turkey for 18 sandwiches, and we have enough cheese to make 15 sandwiches. Even though we have enough bread and turkey, the amount of cheese limits the number of sandwiches we can make to 15. In this case, the cheese is a limiting reagent or limiting reactant. That either term is used in chemistry. The ingredient that runs out first, that limits the amount that can be produced. So in this case, we want specifically a cheese and turkey sandwich. So once the one substance runs out, we're done. We won't continue on. It's specifically for this type of reaction or this type of sandwiches we want. So the limiting reagent controls the reaction and everything else will be left in excess, just kind of sitting there floating around. So the cheese controlled this and we were only able to produce 15 sandwiches. So this situation is very common in chemistry as well as cooking. So if you can relate this to cooking, think of when you run out of one item, you can't, let's say cereal and milk. You only have a little bit of cereal, but you have tons of milk. Well, you won't really have cereal once you have the cereal run out, in a sense, right? If you have Cheerios and you only have 4 tablespoons of Cheerios, once that's done, you just have milk. And that's what this is very similar to, if you can try to think of it as food. For example, the blue flame, so if we see the flame in the corner of a stove, is caused by the combustion of natural gas. What happens is there is more of oxygen available than the methane. Excuse me. I lost my place here. The reaction will take place until all the molecules that are needed to use react. So here we have one mole of methane, or 1 molecule of methane that reacts with 2 molecules of oxygen. When the reaction's complete, we formed CO2 plus HO2. And following the ratio in the balanced equation, we can determine that oxygen is the excess reagent and methane is the limiting reagent. Because methane runs out first, it controls the reaction, it's the limiting reagent, and then we consider O2 as the excess reagent because once we look this over, if you look at these circles, we have oxygen left over in excess, and there is no more of the compounds that made up the methane. They are all used up. All right, so let's take a look at this in even more detail. Let's look at this example. Potassium reacts violently with chlorine gas to produce potassium chloride. If 1.2 moles of potassium are combined with 15 moles of chlorine gas, how many moles of potassium chloride can form? Which is the reagent? Which reagent is the limiting reagent? This sounds really confusing. When you first read this stuff, this seems completely overwhelming. It is not at all what it appears to be at all. You guys have already learned how to set things up to this point, and it's been building up to this point. I'm going to point out one thing that will help you understand what type of reaction you're dealing with that the book's probably not going to point out. This is a limiting reagent problem. You won't always be told that. You will have to know that. How will you know this is a limiting reagent? And I'm going to show you this before we even jump into this problem. It's very simple. You are given both amounts of the reactant. You're given 1.2 moles and you're given 15 moles. In most problems, you're given one or you're given the amount of the product. You're not given both of these. When you're given both of these, you are given them specifically so you can figure out which is the limiting and which is the excess. So the minute you read all these numbers and all these words, don't panic, because limiting reagent problems are the same steps. Doesn't matter how many words are in the problem, doesn't matter how difficult it seems. If it's a limiting reagent problem, you are always given both reactants and you will always follow the same steps for any type of these problems. That's it. So don't let it overwhelm you the minute you read this problem. Remember, chemistry is a self-esteem breaker, but you guys have the knowledge to know to go forward and continue with this. You have all the knowledge there. Don't let this get in your head. Okay, so your book's probably not going to tell you that. That's why I'm pointing this out to you. So in order to do this problem, we need to know which is the limiting reagent. That's the reagent that produces the least amount of product. That's going to control this reaction. That is similar to the cheese. We want to know which is the cheese in this reaction. So we have 1.2 moles of potassium, and based on the balanced equation, we have 2 moles of potassium chloride. That's the product. So we have enough potassium to produce 1.2 moles of potassium chloride. And how do we know that? Because we can look at this reaction right here. And I will go through all of these, but let's go on. We can see from this balanced equation. However, we can also write this more mathematically, where you can write it out right here. 1.2 moles of potassium chloride can be produced. And we can look at the other one. We use dimension. I'm sorry, I'm babbling to myself. I start getting in my own head. So we set up the 1.2 moles. We look at the mole to mole ratio, and they balance out. And you can pretty much tell these canceled out. It's 1 to 1 anyways. This is 1 and 1, these two numbers. So it's going to be what you start with here if these two numbers cancel out. It's 1.2 moles of potassium chloride, but you cancel out the units. Now with the other one, we have 15 moles of chloride, and based on the balanced equation, this is enough to produce 30 moles. We set it up with the 1 mole over the ratio of the 2 moles. That gives us 30 moles. Now, we have to look at the numbers. The numbers are like sandwiches. This makes 1.2 sandwiches. This makes 30 sandwiches. We will have to always pick the smaller number. The smaller number is the one that controls the reaction. And that is going to, you will never get to 30. You're never going to get to 30 because you're going to run out of the potassium that's needed to make that reaction go to completion. The rest of it will simply be floating in the solution. It's never going to happen because there is no more potassium unless you add more potassium, which means that this reaction no longer applies. So the potassium is the limiting reagent or limiting reactant. I'm used to calling it reactant, so if you catch me say it, it means the same thing. It limits the amount of water that can, It controls this reaction and the amount of potassium chloride that can be produced. And the excess reagent will simply be in the solution or left out. In this case, it's a solid and a gas. It will simply just be hanging out because there's nothing left for it to react with. Okay, let's look at another one. Uranium reacts with fluorine gas according to this equation. If 30 moles of uranium combine with 75 moles of fluoride, how many moles of uranium hexafluoride will form? This is a perfect example of a question that's not telling you it's a limiting reagent, but I just told you what the clues are to know that that's what you're dealing with. And that is, you are given both amounts of reactant. Here you are given 30 moles of uranium and 75 moles of fluoride. So it doesn't tell you that that's what it is, but this is exactly what it is. And you go through the same steps of dimensional analysis. Never changes. So in this case, we set up 30, we do the ratio, we produce 30 moles of uranium hexafluoride, and here we do 75 moles with the ratio of 3 moles of fluoride to 1 mole of our product, and it produces 25 moles of uranium hexafluoride. So this is the product. We have a smaller amount of product here. So because this is the smaller amount of product, we have to go back to the reactant. This is the reactant that controls this getting my head again, chemical reaction, and this is the limiting reagent, and the excess is the uranium. So don't get caught up on the products. We're simply using the products so we can see which one of the reagents is the limiting and which one is the excess. Okay, now we're going to look at a new method. And in some reactions, it is easier to use the ice method. In fact, that's the only way I know how to solve some of these is the ice method. I'm sure there's other ways to do it. I learned this as a student as well. And it may look complicated, but it's actually pretty easy to do and use. Okay, so now we're going to look at the previous problem where we had the 80 slices of bread, 18 slices of turkey, and 15 slices of cheese. This means that we can make 15 sandwiches. Now, let's ask another question. If I make all the sandwiches, what is left over and how much after the sandwiches have been made? We're going to use this ICE method, and I stands for initial, and that's how much we have at the beginning before anything's occurred. So we begin with 80 slices. So what you do is you write the reaction out, and you write ICE here, or a triangle. A triangle sometimes you can see, and that means change. And in this case, we have 80 slices of bread, 18 slices of turkey, and 15 slices of cheese. But 0 sandwiches because the reaction hasn't occurred yet. Now we know that the cheese is our limiting reagent. We know we use all 15 up. So I'm going to cheat a little bit and write down minus 15. Why minus 15? Because we end up with 0 cheese by the time all the sandwiches are made. There is no excess left over. In that case, we're going to now look at these two. So if we used 15 slices of cheese, if you write this out, and if this doesn't make sense, you can set this up and write it out like this. So you can see where I'm going with this. I have some samples at the end where I actually work this out so you can see where these numbers come from. This is 15, but I kind of do it this way. So you have 15 used up, 15 with 1 slice because it's a 1 ratio is minus 15. I have a 15 here, but I have a ratio of 2, so it's 30, negative 30. And like I said, set it up like this and you will see where these numbers are coming from. So now we just subtract. We have 50 slices of bread at the end. We have 1 slice, 3 slices of turkey that are left over. We have 0 cheese, and we have a plus. So notice the minus signs and notice the plus sign. And we have 15 sandwiches. So we have increased our sandwiches to 15 by using up all that cheese. But we have 0 cheese left at the end because that's the limiting reagent, and that determines how many we can make. So based on the balanced equation, we were able to not only predict the amount of the product that's produced, but we are also able to find the amount of each ingredient left over. That holds the true same for chemical equations. We can use this for chemical equations, and we will. I have some examples the same way. And I actually break some of these down so you can see. Okay, if 15 moles of HCl and 20 moles of sodium hydroxide are combined, how many moles of each species will be present after the reaction is complete? Write out the balanced equation, put the ice, start with the starting amounts. So you'll always have amounts here, and you'll always have zeros on this side because the reactions have not occurred. When you get to change, that's when the reactions are occurring. So in this case, we begin with 15 moles of HCl, 20 moles of sodium hydroxide. HCl is our limiting reagent, and it's completely consumed up in this reaction. So that means all 15 moles, and this is easy because there's all 1-to-1 ratio. So we can subtract 15 from here and add 15 on this side. This is 0, this is 5, this is 15 moles, and this is 15 moles. And that tells us exactly how much of each reactant and product is used up. Okay, so a summary of this. The limiting reagent is completely consumed. It limits the amount of product that can be produced. In order to determine the limiting reagent, we use the amounts of material present in the balanced equation. The reagent that can be produced the least amount of product is the limiting reagent, so the smallest amount. The excess reagent is not completely consumed. There is always some of the excess left over. Finally, we can use the ICE method to determine the amounts of reactants and products present after a reaction is complete. When do you need to use the ICE? Well, when you're trying to find out what the excess is, you can do it with the dimensional analysis, but it's sometimes time consuming, where if you understand the steps here never really change, you can do it all in one shot and see everything across the board. But it's up to you. This is honestly an easier way than doing reactions like this and working them out and doing them over and over in this for each product, and then trying to figure out what is the amount left over, and then you subtract. It's kind of a pain. So this is an easier way. Write a balanced equation to represent this reaction. Your book seems to like this. I don't. But they want you to count everything. I'm going to jump ahead. So you can see that here is the balanced equation. You have to count these. 1, 2, 3, 4. There's 4. You have 2 molecules of this. How many what is produced over here? We have SO3, and we have 2 of them, and then we have 3 moles of oxygen. Okay, so which is the limiting reagent? There it is. You can count that out. I don't really care for these, but I get the visual that they're trying to show you, that you can obviously see you have more oxygen that is left over after the reaction, and you started with oxygen in the beginning, so it just kind of carried over. I get what they're doing, but I don't know. That's just me. If 5 moles of A and 3 moles of B are combined, what is the limiting reagent? So I've worked out these problem for you. Same steps. Remember I told you, same steps. They never change. The steps never change. And in this case, I have the limiting reagent is A. And you can see it's less amount because it's 2.5 moles of A. And I think I messed that up. I messed this up. That should be a C. I apologize. That should be a C here and not an A. But you can see this would be the lower amount that's produced. So A would be the limiting reagent. If 5 moles of A and 3 moles of B are combined, how many moles of B are consumed? Well, if we look at this, I think I forgot what I did here. This is A, which should be C, and sorry, okay, I now realize they want to do an ICE table on this, and I did not. So there's 3 moles of B, but only 2.5 moles of A are used. So this means that there would be 2.5 moles of B are consumed from the 3 moles of B. So this one I didn't set up correctly because I didn't really look, and that's my fault. I should have paid attention. This was an ICE table one and not just a general one. So I apologize for that. But you have the correct answer, so please set it up with the ICE table and you'll be able to do this. If 30 moles of phosphorus react with 30 moles of chlorine, how many moles of phosphorus chloride can form? And here is 20 moles. So see, sometimes you don't have to use the ICE table. You can, if you're comfortable with it, you can use it all the time. I am so used to doing dimensional analysis. I do it like this, even if I can do the ICE table, because I'm just so used to doing it like this. Hydrogen gas and chlorine gas react violently to form HCl, as shown in the equation. How many moles of HCl can form from the combination of 10 grams of H2 and 50 grams of Cl2? Just because it's grams doesn't mean this is any different. You are given both amounts from the reactants. So again, I probably should have did this in ICE table for you. Didn't even think about it. I'm just so used to doing this. But if you guys need help with this, please contact me. We can work these out together. But you can see that the 1.41 moles of HCl is produced. So that's going to be, and the question is how many moles of HCl can form? And it's going to be 1.41 moles compared to the 9.90. We will never get to this because the limiting reactant will always control this reaction. Okay, if 12 moles of iron and 20 moles of HCl are combined, how many moles of each species will be present after the reaction? So we set this up with the balanced equation. We start out with our initial amounts. The reaction has not occurred, so this would be 0 and 0, which I probably should have wrote in. The slide didn't do that. But let's take a look at how did I get these answers. So where does the 10 come from? The 10 comes from that once you start doing these, believe it or not, you can actually start doing these in your mind. You can see the steps of what needs to be done. But if you are not confident with it, and while you're still learning, I would suggest you still work these out. So in this case, I had 12 moles. I'm looking at my product, and it's a 1-to-1, so I'm going to get 12 moles, right? So why is this 10? Because obviously this must not be the limiting reagent then. In this case, I start out with 20 moles. I set up the dimensional analysis with 2 moles at the bottom, 1 mole at the top, and I end up producing 10 moles of iron 2 chloride. So in this case, I am going to subtract. So I have 20, but I have I'm going to use it all up. So negative 20. I am producing 10 moles of the product. This is a 1-to-1 ratio, so it's going to be 10 moles. I'm going to subtract. I'm going to add 10 moles here and add 10 moles here because these are what's produced. If these numbers, again, are not making sense, do it in the dimensional analysis and you will see where these numbers come from. So in this case, it's 10 moles that are going to be consumed, not 12 because this is excess. This is the excess one. This is the limiting. This is what's going to go to 0. And because this one's going to be a 0, this is not all going to be consumed. So I'm producing only 10 moles. That means that only 10 moles of this is going to be consumed as well. Subtracting, leaving me 2 moles of iron, 0 moles of HCl, 10 moles of iron 2 chloride, and 10 moles of hydrogen. 5 moles of H2 are combined with 0.71 moles of Cl, causing the reaction below to take place. After the reaction, how much of the excess reagent is left over? I did not do this one. I'm giving you the answer. If you need help with this, let's go through it. But hopefully this example of me breaking it down and the example that's in here helps you understand. It might seem intimidating in the beginning, but really the steps do not change on these problems at all.